While consumer video is easy to capture, it suffers from many common artifacts. In this video, we can see overexposed areas and that the video is of limited resolution. In contrast, digital photographs typically have a much higher resolution and are better exposed. Our goal is to bring some of the benefits of still photography to videos of a static scene. To use our system, the user complements a video capture session by taking a few additional photographs. These photographs are used to enhance the video in several interesting ways. For example, here we transfer photographic qualities such as proper exposure to the video. Our system can also modify an entire video by editing just a few photographs or video frames. In this example, we remove the scar on the tree by editing a single video frame. The edit is then automatically propagated through the video. To accomplish this using the input video and photographs, we estimate the scene geometry using structure from motion and stereo. Next, our image-based video rendering algorithm constructs an enhanced video using the appearance of the photographs. The spatial appearance is created while still preserving the temporal dynamics of the video, such as highlights and dynamic lighting. The scene geometry is estimated using structure from motion to recover a sparse 3D point cloud of the scene, and the relative poses of the video frames and still photographs. We then use a novel multi-view stereo technique to estimate the view-dependent depth maps for each video frame. Depths are also computed for each of the still photographs. In the next step of our system for rendering image-based video, we use the depths estimated in the previous phase to warp the photographs into the viewpoints of the video frames. The input video is reconstructed from patches of the warped photographs using a graph cut algorithm. Here we show the graph cut labeling with each photograph represented by a different color. The reconstructed video may contain artifacts. For example, in this reconstruction, we can see holes, seams, and temporal incoherence. Our space-time fusion technique reduces these artifacts by incorporating the temporal gradients of the input video. In our next example, we increase the spatial resolution of the video using high-resolution photographs. Notice the space-time fusion technique preserves the moving window reflections seen in the input video. Since the photographs have a much higher resolution than the video, we can zoom in to view the details captured by the photographs. The resolution is effectively increased by 4 times. In this scene, the dynamic range is beyond that of the video camera. To enhance the video, we captured 6 sets of exposure-bracketed photographs. Using high dynamic range photographs, our system created this final HDR video. In the next example, we demonstrate the ability of our space-time fusion algorithm to transfer dynamic lighting from an input video to a video reconstructed from photographs. Our scene is captured at night on a rainy day. Notice the shadows and caustics from the raindrops cast from a nearby window, and the specularities on the fork. Several photographs of the scene were also taken with long exposure times. Our system produces a well-exposed video while preserving the dynamic lighting of the scene. Notice how, in this close-up, the dynamic lighting is lost when reconstructing the video just from photographs. The space-time fusion algorithm reintroduces these effects, increasing the realism of the scene. Our system can also be used to stabilize a shaky video like the one shown here. Using available commercial software, the motion in the video can be smoothed, but some jitter still exists. Using view interpolation, our system creates a stable tracking motion. We can also easily edit videos by modifying a few video frames or photographs. For example, by simply creating a single matte for each picture frame, we generate a dynamic matte for the entire video. The resulting matte is consistent with the occlusions in the scene. This matte can be used to create a variety of effects such as transforming the pictures to black and white. In the input video, the pictures contain reflections. These artifacts can be removed by inserting a reflection-free picture in each mask. Conversely, we can preserve the reflections recorded in the original video while replacing the pictures. We've also edited the last picture frame in this example. Effects can also be applied to entire photographs. For example, here we apply a painterly effect to our input photographs. Our system can then render a video using these photos. Here are some examples using other effects. Applying the same effect to each frame independently produces flickering artifacts. Here is a video sequence of a flower shop. Unfortunately, the no parking sign is unattractive and includes much of the scenic background. The user can select the no parking sign and the pole in a single video frame, and the system removes them from the entire video. To produce this effect, our system fills in the background by projecting the colors from neighboring video frames using the depth estimates. We have shown how several still photographs can be used to greatly enhance and edit a video sequence. Here again are a few of the examples.